We're looking at binary arithmetic. Why the hell are we looking at binary arithmetic? What is binary? Does everyone know what binary is? Counting system that has how many numbers in it? 2. Okay, so how is that useful for us to know some binary arithmetic? How is that going to help you in electrical engineering? Should have an idea of that already because we talked about digital circuits on Monday. And those digital circuits use voltages which are high or low levels, which can be quite easily representing numbers in a binary counting system. Okay, so there's the tie-in. Okay, so we want to, at the end of today, you want to have an idea of why computers use binary. I've already given the most compelling answer to that. We want to be able to convert numbers between a number of number systems. Decimal, which is the one we're most familiar with. Binary, which we will become very familiar with. And some not so mainstream ones, such as octal and hexadecimal. Which are both useful, particularly in electrical engineering and anything to do with programming. Want to distinguish between parallel and serial transmission. The name is very self-explanatory when we come to that. I'm going to give you another couple of ways to represent numbers, which two of which are called BCD, which is called binary coded decimal, and something called grey code, which is used widely throughout electrical engineering and in some systems of mechanical engineering. And we want to be able to perform additions and subtraction of binary numbers. Why do we want to do that? Because if you know how to add numbers in binary, we can construct digital circuits which can add binary digits together, because binary numbers can be represented as voltages. How does that help us? Well, you build one little thing called an adder, and you stick a whole load of adders together, and these form the basis of modern computers. Okay? Modern computers, well, computers are, as the name suggests, they compute things, and addition and subtraction are the most simple computing operations. Okay, so we know now that information comes in many forms, and we transmit information or transfer information between each other using a number of mediums. We use characters on a page or an email. We use numbers to convey size of things. We have visual and audio signals. And another way to do this is, apart from what we've learned so far using analog signals, is digital systems. Of course, how do we do this? Well, first, we need to encode whatever information we want to send as digital values. So that's not straightforward. So I've told you that pretty much all signals are continuous, and then I haven't told you how you convert these into a digital form, and in fact, I won't go into that too much. Suffice to say that we do something called encoding. And once we've encoded these into digital values, we then represent these values as, say, electrical voltages, which we can then transmit these voltages between 2 points. And these voltages are transmitted not as signals which can take on any value. They are transmitted as signals which can only take high or low values. And we saw why that is the best way to do things last lecture. Okay, and at the end, we decode those received voltages to recover information. This is all very simple conceptually. In practice, there's a whole field of engineering dedicated to making these systems work, telecommunications engineering. So simple conceptually, in practice, quite a bit harder. Okay, so here's their example we took from Monday. Let's say you had this, well, let's say we wanted to encode some characters, which I've got in green, say the letter A and the letter B. We use international standard ways of doing this. So who's heard of ASCII? Yep, some people have heard of ASCII. For those who haven't heard of ASCII, it's a standard way to encode all alphanumeric characters and some special symbols into corresponding numbers. Okay, so the letter A in ASCII, the capital letter A is encoded to 65 as a decimal number. Or instead of, if we wanted to encode characters, we could use that. If we wanted to encode a signal, what we would do is we would take this continuous signal in grey and run it through what we call an analog to digital converter, and that would give us this red signal out. All right, and this signal would then be translated into a string of numbers. Okay, so this signal could be represented by a string of numbers corresponding to the red values. So that would be like 4, 5, 4, 3, 4, 6, etc. Okay, so that's two ways we can get information into a digital form. So currently this digital form is in decimal, but what we next want to do is convert that into binary, because once you have it in binary, you can start sending it across a distance, say using electrical wires or through wireless signals, and have that received on the other end easily. Okay, so more fundamentally, our brains like to work, and we've been taught to work in a base 10 numerical system with 9 digits. The reason for that being widely accepted is that we have 10 fingers, and it made it easy for us to learn and count. Digital systems have 2 states of voltage, so naturally this is best represented using binary, and that's why it's important. And binary has 2 symbols, 0 and 1. Note that we always start our counting systems from 0. Okay, so in decimal, 0 is usually our first digit, and we count up to 9. In binary, 0 is our first, we count up to 1. When we talk about octal, there are 8 octal symbols. You count from 0 to 7. Who's heard of hexadecimal? Hexadecimal has 16 characters in it. You count from 0 to 9, and then when you get to 10, you represent that as a letter A, and you keep going up to 15, which represents the letter F. Okay, so anyway, once you've converted that string of numbers into a binary set of numbers, then the next part becomes hardware, where we transmit these as high or low voltages across a wire. Okay, and you can do that using, you could do that using knowledge that you've gotten up to this point in ENG1030. You could construct a circuit that takes some input and would give you either a high voltage or a low voltage, depending on what that input is. And you can do that with an op-amp, in fact. You can make the op-amp in differential mode, and you could make the op-amp go all the way up to its positive supply rail for one symbol, or all the way down to its negative supply rail. And you'd have a binary signal. Okay. So, how do we represent numbers in binary? Well, if you consider how we represent numbers in decimal, it's exactly the same. Just looks a bit different because our minds don't usually work in bases of 2. It usually works in base 10. So let's say we have this number, 143.27. Now I've got this little 10 here as a subscript. We never write this in general usage because we always assume everything is in base 10. Now that you're talking about digital systems, it's important to know whether you're working in base 10, base 2, base 16, or base 8. Okay? So here, I've written this 10 here, subscript, to represent that. So 143.27 really means that, well, also the other important feature here is we've got a decimal point. And this decimal point is, well, if you think about what the decimal point does, it gives you a reference for where 0 is, right? And any numbers to the right of the decimal point represent something. The numbers to the left represent something. Okay, so it gives you a point of reference. So consider this number. This number means 143.27. That means that there are 3 lots of 3 lots of 10 to the 0. What is 10 to the 0? 1. So there are 3 lots of 1. There are 4 lots of 10 to the 1. And there is 1 lot of 10 squared. Does that make sense? So you add those 3 together and you will get 143. If you consider the digits to the right, then you can say there are 2 lots of 10 to the minus 1, because that's 0.1 times 2, and there are 7 lots of 10 to the minus 2, because 10 to the minus 2 is 0.01. Now, if we add all those together, then this number represents, if I write this down in this notation, it represents 143.27. Now, we do this naturally ever since we've learnt numbers, from when we were in primary school. It's no different when we're representing numbers in binary, okay? So if you have a look at this number, we've got this subscript 2 here to avoid confusion between bases, because 1101.01 in binary means something completely different to 1101.01 in base 10. Yes? So here we've got a binary point. There's a decimal point. We'll call it a binary point. And that serves as the same thing. It's a reference point. So numbers to the left of the binary point, if you will, follow the same logic as for decimal numbers. Oh, sorry, all the digits follow the same principle. So here you've got 1 lot of 2 to the 0. You've got 0 lots of 2 to the 1, 1 lot of 2 squared, and 1 lot of 2 to the 3, 0 lots of 2 to the minus 1, and 1 lot of, oops, that should be a 1, 1 lot of 2 to the minus 2. So if we add up what all these values are, this equals, so here, this equals 8, this equals 4, this equals 0, this equals 1. 2 to the minus 1 is 0.5, because it's 1 over 2, and 2 to the minus 2 is 0.25. Okay, so this number here actually represents, in decimal, 13.75 in base 10. Yep? Sorry? Oh, yes, you're right. Sorry. Whoever wrote these lecture notes is an idiot. That person was me. My fault. Yeah, that should be a 0 there. So that's not quite right. That'd be 25. Okay? So I'm assuming we're all up to speed on this. So let's keep going. That's an easy way to convert from binary into decimal. How do we convert from decimal into binary? This is not so trivial. There are a number of methods you can do this. This method may be a little bit slower, but it always works. Other methods involve carrying powers of 2 in your head and finding how many of these fit together. But I think it's safer to give you a tried and true method. So if I want to convert this number 143 base 10 into base 2, the easiest way to do this is to follow this algorithm. What's an algorithm? An algorithm is a set of instructions or a method to do something, yes? Okay, so this is the method to convert from decimal to binary. So you take your number, and pay attention because you're about to do this shortly in melts. So you take your number, you divide it by 2, and you write down what the result is after you divide by 2, and you write the remainder. Who ever thought these things would be useful ever since we learnt division? All right? So this remainder will always either be 1 or 0, because you're dividing by 2. There's always going to be either a remainder 1 or a remainder 0. So it makes it a little bit easier. So you write down what the remainder is, you write down what the quotient is, and then you repeat. So you've got 71, and you divide it by 2, you get 35 with the remainder 1, because this is an odd number. And so on and so on. So you take 35 divided by 2, and you get 17 with remainder 1. Getting a lot of remainder 1s here. 17 divided by 2 gives us 8, because 2, 8 to 16 with the remainder 1. 8 divided by 2 gives us 4 with the remainder 0. Okay? So now what? Do it again. 4 divided by 2 gives us 2 with the remainder 0. 2 divided by 2 gives us 1 with remainder 0. And finally, we have 1 divided by 2, which signifies, well, we get a quotient of 0, okay? And this signifies that our algorithm now stops, okay? So you don't need to go any further. And you have a remainder of 1. Note that you'll always come to this step. There'll always be a 1 divided by 2 giving us a 0 with a remainder 1. Now, how does this help us? Well, this helps us because we just read back these binary digits, or these bits as we call them, backwards, and that gives us the number. Okay, so over here, if I go backwards, 1, 0, 0, 0, 1, 1, 1, 1 is 143 in base 10. Okay? Now, if you work the other way around, you would see, if you wanted to convert back the other way, you would see that this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, up to 2 to the 7 up here. And you would add together lots of these, and you would see that it would come back to 143 base 10. Okay, so, oh, and also, a bit of terminology. The bit that represents the largest power of 2, so over here, this is 2 to the 7, all right, where we've got our binary point here. So this is 0, 1, 2, 3, 4, 5, 6, 7. This 2 to the 7 is called the most significant bit. Okay, it's most significant because it's the biggest. And we like to say big things are most things. Just because, I don't know, I just made that up. Anyway, that's significant, pardon the pun. Okay, and the least significant bit, as you might guess, is always the bit next to the binary point. We call that the least significant bit. It just helps us because sometimes when you give a number to someone, well, by someone I mean a computer, some computers work from different ends. Some computers will take the first bit that you give it as the most significant. Some computers will give the least significant bit as the first bit that you give to the computer. Okay, so here's a question. Quickly convert this into binary for me. And I'll put that up on Melts. So this shouldn't take you too long. I'm not going to give you much time. Do you think this should end in a 1? Should the least significant bit end in a 1 or a 0? What do you think? Why should it end in a 1? Because it's an odd number, yeah? So 2 to the 0 is 1, and so because the number's odd and all the other powers are even, it really should end in a 1. Okay, who needs more time? No? Nobody needs more time? All right. Closing the quiz in about 10 seconds. Don't put anything that ends in a 0. All right. 5, 4, 3, 2, 1.5, 1, 0. All right. Wow. 4 people jumped in and that was 0. Okay, so what is it? It is, in fact, well, it's down here. That's where it is. It's, in fact, 1101. Okay. So you've got 2 to the 0 here, 2 to the 0, 1, 2, 3, and 2 to the 4. So what's this? 16 plus 8 plus 1, yes? Equals 25. If you got this one, then this one would be 16 plus 2 to the 1, which is 2, plus 1 equals 19. Okay, so not quite right, but good try. Next, do it the other way. What's this? I'll give you a chance to answer in half a second. Go for it. So should this be an odd number or an even number? Odd, yes, because you've got a 1 over here. So don't be picking D. Okay, 10 more seconds. You'll get really good at powers of 2 by the end of this lecture. 2, 4, 6, 8, 10. That's not powers of 2. Okay, 5, 4, 3, 2, 1. Lock. Ah, my phone just turned off. Lock. Okay, so what do we got? Oops, hold on. What did I do? Oops, I switched team mode on. Let's turn that off. Okay, so we get this one. 13. Is that right? So what do we got? 2 to the 0. Whoops, I won't even bother writing 2 to the 0. 2 to the 0 is 1, plus, what's this? 2 to the 2 is what? 4, and what's this? 8. So 8 plus 4 plus 1 equals 13. Well done. I know the people who did this were just messing with me. It's all good. Yeah, there was 5 of you. All right, good. So I think people are got that down pat. Okay, so now you know how to convert numbers into a string of bits. Well, what do strings of bits mean? Okay, so in digital systems, we call every binary digit a bit. That's where the term comes from. And all computers, or useful computers, deal with groups of bits at once. Okay, and the number of groups, the groups of bits that they deal with at once typically tends to be, unsurprisingly, also in powers of 2. So it might be 4 bits, 8 bits, 16 bits, 32 bits, or 64 bits at once. So who's heard of a 32-bit processor? Who's heard of a 64-bit processor? That's what we're talking about. It means that these computer processors take in blocks of X number of bits, 64 bits or 32 bits at once, when they're considering numbers and calculations and transferring data. They do this in blocks of bits. Usually, instead of saying, oh, this is a 4-bit word, or this is an 8-bit word, or this is a 16-bit word, we have specific terms for these. A 4-bit word is often called a nibble. Why is that? Because it's half of a byte. And if you take a really big byte, you might call it a chomp. Okay? This is the one that you'll probably be most familiar with, because that's how much, because all of your quota are on your mobile phones when you're transferring data and you have to pay for it. It's measured in bytes, right? Okay, so a byte is 8 bits worth of data. Okay, so if I have an 8-bit word, this can represent 2 to the 8 distinct values. So if I have an n-bit word, it represents 2 to the n. So if I have 8 bits, or 1 byte, how many distinct values can that byte hold? So what's 2 to the 8? 256. Okay, see, I told you you'll start to get good at powers of 2. Okay, so this is the key, this is something to remember. So, your 32-bit processor, how many bytes, how many bits can that hold? 2 to the 32, right? So that's how many distinct values this 32-bit word can hold. Incidentally, does anyone know what 2 to the 32 is? Yeah, it's about 4 billion or so. Yeah, it's actually 2 to the 30 times 2 to the 2. You can do some multiplication, and 2 to the 30 is 2 to the 3 times 2 to the 10. So this is 2 to the 2 times that times that. So you could be 4 times 8 times 2 to the 10 is 1024. So 2 to the 10 is about 1,000. So you start multiplying these out, and you start... Oh, hold on, no, that's not right. No, that's addition. Yes, that's right, my bad. Scrap that. Wow. Ah. Yes, it's 2 to the 30 times 2 to the 2. Yes, okay, I'll leave it at that. Okay, next thing. We're really getting through a lot of concepts today. You can transmit stuff or information in serial or parallel. These are the 2 main schemes we transmit data in. A parallel transmission means that you break up information into a number of streams and you transmit them all at the same time. And that's why you get the word parallel, because as you transmit them, they look like they're moving in parallel directions. So let's say I have a word here, and that word might be, 00, whoops, my pen's not writing. That word might be 0011, 1101, and I would break this into chunks, and I'd send them all in parallel. So I could break this into 1 chunk here, corresponding to this, and I could send them all at the same time together. And the transmission time required to do this is the time that it takes to send 2 bits here. So that's fast, right? As opposed to the other way, which is called serial transmission, where if I take that same sequence of bits and I want to transmit them all one after the other, then the transmission time here, as you can see, is, by the length of the lines, about 4 times greater than if I sent it in parallel. What is the disadvantage of sending in parallel? We need more lines, right? So over here, I need 4 lines to send 4 bits in parallel, plus I actually need another ground wire. Or if you remember from op amps, you could do this in twisted pairs. So you'd actually need 8 wires. Contrast this to serial, where I can do everything with 1 wire or a twisted pair, which would be 2 wires. So depending on the application, do I need to get data really fast from one end to the other? Or is it sufficient that I just transmit data one bit after another? So in actual fact, you probably haven't come across them, but there used to be things called parallel cables. Anyone come across those? On printers? Yes? So printers, because they send a large amount of data from the computer to the printer really quickly, because people don't want to wait 2 hours for their printing to occur, use parallel cables. Whereas if information can get there a little bit slower, you need to send less of it, you would use a serial cable. Who's heard of RS-232 cables? Yeah? So that's the difference. And if you chop them, you'll find that there are, in fact, 9 individual wires in a parallel cable, and there are 2 wires in the RS-232 cable. Okay. Other base representations. So we've done 2, we've done 10. There are other ones we use in computer systems. I just want to make you aware of them and show you how you can quickly convert between them. The other ones are called hexadecimal, which I told you about, and that's base 16. And another one's called octal, which is base 8. Why on earth would we want to do this? That's a good question. I have a good answer in a couple of slides. But before that, here are the symbols which are used for those different base systems. So this is a good reference slide. Hex, and this is the shorthand. Hex, dec, oct, and bin. Okay, so hexadecimal goes from 0 to F. Okay, and F represents 15. How do you convert between these? Well, a little bit tricky to convert from decimal to octal or hex because it's hard. Our brains aren't very good at doing computations in base 8 and base 16. What is 8 to the power of 12? What is 16 to the power of 3? No takers? Okay. That gives you a good idea of why it's very hard to do decimal to octal and hex. So the way to do it is we can convert from decimal into binary and then from binary into octal or hex really easily. Okay? And the way you do that is you chunk a number of bits. So for example, I want to convert 348 into octal and hexadecimal. Well, I would do this using a halfway method first, which is decimal to binary. With a little bit of practice, you can do this one pretty quickly. 348 into 101.0111000. I reckon give you 10 minutes of doing this repeatedly, and you'd get pretty good at it. Next, to then quickly convert this to octal, you take this string and you break it up into little chunks of 3 bits. Okay, so I take this string and I chunk this into 100, take this, chunk this into 011, take this, chunk it into 101, and then I've got 3 chunks here. They're in green, blue, and red. And what do these represent? Well, 100 in binary represents 4, 011 in binary represents 3, and 101 in binary represents 5. And hey presto, you've got your octal representation of 348 in octal. Okay? 534. How do you do this for hex? Well, instead of chunking 3 bits, you chunk 4 bits. That's the difference. Okay? Now, notice I've got leading zeros here because there weren't not enough zeros in front here. So I would take this chunk, this chunk here, and I take this 1 and put some zeros in front of it. And then I take these values. Now I've got 1100 here. What's that equal to? 8 plus 4, right? Equals 12. And the 12th symbol of hex is C. Okay? Over here I've got 5. Well, the 5th symbol of hex is 5. And over here I've got 1, and that first symbol of hex is 1. So converting from 348 into 534 and 15C is done using binary in the middle. Okay, so hex and oct are convenient representations of binary values. This is why we use them, because who's heard of a MAC address on an Ethernet card? Who's heard of Ethernet? Okay, good. So an Ethernet card is what you plug that blue network cable into a port on your computer, maybe a laptop or desktop. You plug it in there, and every single one of those network ports is called, well, Ethernet ports, has a specific, unique number on it. And that number is represented by, well, it's a number, but it's most often represented as a binary value. To a computer, all it is a binary value. To a human, I don't want to remember this string, right? Because our working memory tends to be about 7 digits at best. Well, 7 digits if you're not inebriated, less if you are, and if you're a bit of a genius, maybe you can do about 10 to 13, okay? So instead of trying to remember this giant string of ones and zeros, you could just remember this string of hex. And it's chosen because it's convenient to remember. Okay, so this, if I chunked all these into little 4-bit sections, right, and converted to hexadecimal, it would give me something that I could very easily remember. Bad ace, okay? Very good multi-choice thing to put in when you don't know what you're doing. Okay, so that is why we use octal and hex. Octal we use in internet numbering sometimes. Hexadecimal we use a lot with hardware, computer hardware. Okay, how do you convert back? Oh, question?
Yeah, what's the answer to the gate?
Sorry?
What's the answer to the gate?
Oh, okay, yes, sorry, I forgot to go for the riddle. So, why is Halloween the same as Christmas? Does anyone have an idea? Sorry, not people who've repeated the unit. Did you didn't repeat the unit. Okay, so why are they the same?
Because oct31 is equal to dec25.
Very good. Yeah. Oct31 is equal to dec25. Yes, very good. Did you know? Did you hear that one before, or did you know? Did you just work it out? You went, oh. Very good, very good. Yeah, funny how it worked out that way. Yep, so you are officially the best geek in the room. All right. How do you convert back? Converting back is simple, exactly the same. You've got over here B, which represents 11 groups of 16 to the 0. You've got one group of 16 to the 1, and you've got A groups of 16 to the 2, where A represents 10. Okay, and that gives us this number. Octal, same thing, just work in base 8. Okay, so that's octal and decimal, hexadecimal. Here's another scheme which is convenient in engineering. It's called binary coded decimal, and this is simply where we use 4 bits here to represent our number, our decimal number. So 0 is just represented by the binary value of 0, 1 is represented by the binary value of 1, etc., up to 9. And this is used because it's easy to interpret. So if I see a string, if I see sets of 4 bits, so if I see 0, 0, 0, 0, and then I see another set of 4 bits, 0, 0, 1, 0, another set of 4 bits, 0, 1, 0, 0, I can quickly say that that's 0, 2, 4, right? It represents 24. And that's really all it's there for. It makes a nice, easy numbering system for humans to interact with computers. The only disadvantage of this is less efficient for storing large numbers, because if I want to store 103.5, for instance, I would need 16 bits, one for each digit, whereas 103.5, if I stored it in native binary, would only require 8 binary bits. Okay, so you're using more bits to make it more human readable. So computers don't work with this, but a lot of hardware which is human and computer interfacing, so where humans need to read it, often use binary coded decimal. Another way you can encode numbers, grey code. Okay, this is a little bit subtle. This is where we encode a particular state, so it doesn't need to be just digits, but digits can be states, using a specific ordering of the bits. So over here, I start with 0, and that's encoded as 3 0 bits. And now I start to encode the next numbers in a special way. The special way is that no two bits, only one bit is different between any two adjacent binary codes. So between this state 0 and this state 1, only this least significant bit changes. Between state 1 and 2, only these two bits change, the second most significant bit, and so on. So you'll notice that between any of these two rows, only one of these bits will change. Okay? The other two bits remain the same. Okay, so you think this is a bit strange. Well, it's actually got a number of applications, particularly states in mechanical systems. These are used in a number of things, which you may or may not. These may or may not mean anything to you. Positional encoders in robotics, genetic algorithms, error correction codes, and something we will come across, Carnot maps. Okay, next week. So that's why there's a quick intro into that. Whew. Okay, I'm not going to do these because I'm probably going to run out of time. There are 2 MELTS questions, but I'm not going to put them up, so you don't know them. But I strongly suggest you do these in your own time. Okay, so you want to convert, what's this, in base 16. In fact, you could do this pretty easily on top of your head. Actually, I'll do it now. So this is 2. This is D, and this is 1. So it's 1D2. Okay, and here, 25 in BCD. Well, what's 2? 2 is 0, 0, 1, 0. And what's 5? 0, 1, 0, 1. Right? So that gives us C. Okay. Sorry? Oh, B, yes. My bad. Okay. Okay, finally. So this is the last, I've got about 10 minutes to do this, so you'll get lots of practice on this in the tutes. How do we add numbers together? So let's say I've got 2 binary numbers, 1011 and 1011, and I need to add them together. How would you do this in decimal? Well, go back all the way to primary school. How do you add like 10 plus 23? Well, actually, that's not an easy one. Well, sorry, that's too easy. Let's say that, right? Because this one's got some carry. You would go 0 plus 3 equals 3, and then you would go 3 plus 8 equals 11. Ooh, but 11 has to carry a 1 over somewhere. So I put a 1 here, I put a 1 here, and I bring down that 1 to give us 113. Same thing in binary, except in binary, it's slightly easier. Well, depending on how you look at it. Because in binary, there's only a number of ways you can add up 2 bits with a carry. Okay, and that's 0 plus 0 gives us 0. 1 plus 0 gives us a 1. Now, 1 plus 1 gives us, what's that in decimal? 2. And what's 2 in binary? Well, it's 1, 0. Okay, so that's where you start getting your carries over. And then you can complicate this by saying, what's 1 plus 1 plus 1? Well, that's 3. So 3 in binary is 1, 1. So I want to add these together. Well, I'll take these 2 bits. I go 1 plus 1 equals 1, 0. So I put a 0 here, and I carry the 1. I'm just writing the 1 underneath because it's easier to put in PowerPoint. And then I've got the next most significant bits. So I've got 1 plus 1 here. That's 0, but I have to carry this 1 here. So that gives us a 1. And I have to carry the 1 from that because I have an extra 1 because it's 1, 1. Sorry, 1 plus 1 plus 1. And do the same here. So 0 plus 0 gives us 0. Carry the 1 from here gives us a 1. And because we don't have to carry here, now we've got 1 plus 1 gives us 1, 0. Yeah? So this gives us 0, and carry the 1 across gives us 1. Okay, so that's how you add 2 numbers together. Real easy. We can all do it. And in fact, we can design a logic circuit, which you will do in a couple of lectures, to actually carry out an addition operation along any number of bits. Okay, so Also now, this is where words come into it. So if we're working with a computer with word size 4, and I took two words of size 4 and I added them together, well, it turns out that this 1 sort of drops off because you can't represent 5 bits with a computer that only can compute 4 bits at once. And when this happens, it's called overflow. Okay? So have you ever heard of a have you heard of an overflow error? That's when often happens when you get two numbers which cannot be represented, or it wraps around to give you a different number, and I'll come to that later. Okay, so great, you can add numbers. How do you subtract numbers? Now this is the key thing. First, to subtract numbers, you've got to have to be able to represent a negative number. I can't subtract positive number. Oh, hold on, what's negative? Because, well, I'll tell you why you can't do that. Because A minus B is actually equal to simply A plus minus B, right? Okay, is there any incorrect logic there? I hope I haven't. Well, if there is, then our mathematical system is not worth using. Okay, so to be able to do subtraction, you need to be able to represent a number by a negative value. Otherwise, you can't do subtraction, because if we can only represent positive numbers, you can only add positive numbers. Okay, so it turns out we can use, because of this, where A minus B is equal to just A plus a negative value of B, we can actually use the same addition circuit to do subtraction, because you're just adding a negative representation of a number. Okay, so from that logic, A plus minus A must equal 0. So how can we represent a negative number? Well, there's a couple of ways you might think to try this. Maybe we introduce a sign bit. So you add a little bit at the front, which is 0 when the number is positive, and it's 1 when the number is negative. So this number here is 5. And we're saying that 0 represents positive, and over here you've got this negative 5. Okay? Good way to try. Let's try it. If this were correct, then this must be satisfied for any good mathematical system. A plus minus A equals 0. Does that work here if I use an adder circuit? If I add these two numbers together, what do I get? Oops. I get 0, 0, 1, 0. Not so good. That gives us 2. So it's saying 5 plus minus 5 equals 2. Okay? If I can produce a computer that does that and is useful, then I don't know what that means anyway. Okay, so no good. Which is not 0, so that's bad. How about we invert all the bits to represent a negative number? That might be a good idea. So if I inverted all the bits from this, and I inverted them all, I would get this. What if I add them together? Then, we get something which is a little bit interesting, right? All ones. And in fact, if you did this for all numbers, any number, you would get a whole load of ones, no matter what number you chose. So it's close, but let's do something interesting. We add 1 to this, and we overflow the result, and that would give us 0. So if I go 1, 1, 1, 1, plus 1, then I would get 1, 0, 0, 0, 0. And if I threw this bit away, then our numbering system works. Yes? Okay. So, how do we subtract two numbers? We convert a number to its negative, and this is I'm summarizing the process that we just did. And that is, first, we invert all the bits. When we do this, it's called taking the ones complement of that number. So here's 5, and this is the ones complement, and this is the ones complement of 5. Then we just add 1 to it, and this result we call the 2's complement. Okay, the 2's complement. So this is 1010 plus 1 gives us 1011. Now this number is the negative value of the original number. Okay, so this number here is equal to negative 5. That's how we represent a negative number. And the reasoning behind this is because when we add these two numbers together using an adder circuit, we get 0. which is as it should be. And this works for all numbers, which is a requirement. So how do we know if a number is negative? Well, in this system, a number is negative when the leading bit, the most significant bit, is equal to 1. Okay? So if we know that a number is negative, so over here, we know this number is negative because it's got a leading 1, then what is this actual number? How do we find out what it is? Because we know it's negative, but if I go back and I try to say, oh, this is 2 to the 0, 2 to the 1, blah, 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 it won't work. So to get the original number, we need to take the 2's complement of the negative number to give us the magnitude of the negative number. So here, you've got 1, 0, 1, 1, 0, 1. That's, oh, we say, oh, there's a 1 here. We know it's negative, right? So how do we know what number it is? Well, we take its 2's complement, and then we find the magnitude of this, which is 19, okay? And so thus, this number here is equal to negative 19. Okay, so I think that's all we've got time for. I might finish this off at the beginning of next lecture. Okay, so thanks. Mindful of the time. See you on Thursday.